Hey guys, and welcome to another video. I just wanted to do a quick tutorial on how to solve an eigenvector decomposition problem. There's not going to be any theory in this, it's just going to be the solutions. If you're looking for theory, this is not the best channel for that. So, mostly just like a helpful classmate on this one. So let's start. Usually when we're doing when we do characteristic root test, which is finding the lambdas, when we want to confirm either a maximum or whatever, minimum, whatever we think we're looking at, we start off with a function, right? And usual steps, first order condition, so involves taking the first derivative with respect to our variables. In this case, we have a 3-variable function, f of x, y, z. And so let's go ahead and start with the first step. So taking the first order condition, taking the first derivative of the function with respect to each variable. So we can go ahead and do that for f of x. 3x squared, right? Won't go through calculus rules here, but I'll assume that you know how to do this. So minus 6x plus 3. No other x's left, so let's move on to y. Oh yeah, and of course they all equal 0. Move on to y. 10y plus 7z and minus 55. And no other y's. Now we can go ahead and do z. 7y plus 10z minus 64. And now we want to solve for the stationary point or points if there's more than one. I think right off the bat we can solve for x right away. It's a quadratic equal to 0, so we can go ahead and drop in our quadratic formula. So let's go ahead and get that done, which should be 6 plus or minus the square root of 6 squared minus 4a, in this case it's 3, 4ac, right, over 2a, which is 6, so both sides over 6. Let's get my calculator because my mental math is not strong. 6 squared minus 4 times 3 times 3 is 0. Okay, so we're going to just have 1 plus or minus 0. So we know x equals 1 and nothing else, so x is solved. And let me get that highlighted just so it's clear. Oops. All right, to solve for y and z of our critical point, we can just do elimination substitution method. So we can just jot these down. On this side, 10y plus 7z equals 55, right? Because they're both set to 0. And then 7y plus 10z equals, oh, I forgot the other 5, equals 64. And then we can multiply the bottom row by, the top row by 7, 70y plus 49z equals, I don't know what 55 times 7 is, let's see, 385, and the bottom row by 10, so we have 70y plus 100z equals 640, and then we'll do the bottom row minus the top row, which will give us 51z equal to 640 minus 385, that's 255, divided by 51, gets us z equal to 5, and now we can plug that, let me highlight that before I move on. Now we can plug that z equals to 5 in any one of the other two equations to solve for y. So let's go ahead and just do it in this corner here. I'm going to make sure that's still in the frame. Put it up a little bit. All right. So do 10y plus 7 times 5 equals 55. What is 7 times 5? 35. And then 55 minus 35, 20 divided by 10, that's 2, right? Y equals 2. So now we have our critical point, and we're going to move on to the third step. So let's go ahead and write this here. The Hessian point, we want to do a Hessian matrix is a matrix that's made up of all second derivatives. Okay, so as we see here, f with respect to x twice, f with respect to yx, zx. So each row is going to be x starting with x, then starting with y, and then starting with z. And so we're going to calculate the second derivatives of all these equations at the specific point where x equals 1, y equals 2, and z equals 5. Okay? So let's start with f of x. F of x, we can see that if we take the derivative with respect to x again here, right, we're going to get 6x. Maybe I'll write that in purple underneath or next to it, let's just say, just so we're a little clear on what we're doing. So f of x, right, so we're taking the derivative again, is going to be 6x minus 6, and it's at point where x equals 1. So it's just 6 minus 6, and we can go ahead and drop in a 0. So, right, 6 minus 6 at x equals 1 is 0. And I realize this matrix is going to be way too big if I'm making the numbers that small, so let me just try and make it a little bigger. All right, so fyy, well, there's nothing to solve at point 2, because if we take the second derivative of fyy, I'll put it here, and I won't show you, you know, or actually I should have done fxy first. Let's just say there's no y in this equation, so the derivative is 0 with respect to y, and then there's no z in the first f of x either, so it's also going to be 0, right? There's no z here. We're starting with fx, right? fxx, fxy, fxz. And since y and z are not in this, it's going to be 0 for both. Okay, so let's move on. Fyx now, there's also no x in fy or fz, so we know right away that this is also going to be 0. Now when we do double fy, right, it doesn't matter if it's at point 2 because, well, there's only one y term here, and once we take the derivative, it's just going to be a constant at 10, right? So we can go ahead and drop that in, and I think you get the point. We can go ahead and finish everything up much faster. So fzy, only one y term here, and that's 7. Fzz, the only z term here is 10z, so we're going to be left with 10. And then finally, fyz, and there's only one z term, and that's a 7. Right, so now we have our Hessian matrix. That is the matrix of second derivatives at the point x equal to 1, y equal to 2, and z equal to 5. And so now we can move on and start with step 4, where we're going to solve for our lambdas. And normally when we have our lambdas, we're doing something called the characteristic root test, in which when we look at that, let me bring back the Hessian really quick. When we're looking at this Hessian, we do something called a leading principal minor test, which I'm not going to go over here. And essentially, the leading principal minor test will, and I'll cover that in another video probably, will tell us the definiteness of our function at this point, whether it's semi-definite or semi-definite positive or definite positive. Basically, it's telling us is it a max or min? Are we sure it's a max or a min? Or is it nothing? You know, is it indefinite? Is it a plane? Is it an inflection point or something like that? A plateau. So the characteristic root test, which is what the lambdas tell you, is another way to confirm whether max min or positive definiteness if it's a minimum, or positive or negative definiteness if it's a maximum. So if we want positive definiteness, we want all our lambdas to be positive. If we want negative definiteness, we want it to be all negatives. And if there's any zeros, then we have semi versions of those. And if there's mixed positives and negatives, well, then we have some type of plateau, and we don't have a max or min. So we want our lambdas. We want the determinant of our matrix. And by the way, this matrix here, when we're looking for the lambdas, we're going to take our Hessian matrix. That's what we, at the stationary point that we had just solved in the last part, and we're going to subtract down the diagonal lambda from each term, only down the diagonal. And then we want to find a determinant of this matrix, where the resulting determinant from this matrix, which we'll call A, because I've written determinant of A. We want to find lambdas where the determinant equals 0 for our matrix A. Okay, and we're going to have one lambda for each variable of in our function. Okay, so we need to find the determinant of a matrix, and we know that it's it's alternating signs of plus, minus, plus, and then we do the A times B minus C times D. You can go ahead and Google the formula how to determine the determinant of a matrix. We won't go over that here. So let's start. So we're going to have negative lambda, right, times 10 minus lambda times 10 minus lambda, and minus 7 times 7, which is 49. Okay. And then this is going to equal 0. And luckily for us, the other two column starting positions are both 0, right? So we don't need to bother calculating the other I don't know what you call it, the other areas that are multiplied by zeros. So we only need to worry about the negative lambda here and this square to find the determinant. So anyways, right away we can see that whenever we see this, we know we're going to end up with some sort of quadratic. So we're solving for lambda right now. So let's go ahead and find out what this quadratic is, because that's going to help us, right? We have 10 times 10, that's 100, minus 10 lambda, minus 10 lambda minus 10 lambda. All right, 10 times 10, 10 times negative lambda times 10, and then finally negative lambda times negative lambda. So that's plus lambda squared minus 49 equals 0. Because this equals 0 and we want to solve the quadratic, we already know that for this expression to be true, right, lambda can just equal 0, because we have this whole expression here multiplied by lambda, and that has to equal 0. So we know that one of our lambdas can equal 0. So right away, we can find that lambda 1 equals 0. And we can actually divide this expression by negative lambda to find out what the other two lambdas, lambda 2 and 3 are, so that we're left with just the quadratic. So we can divide by negative lambda on both sides, and 0 divided by anything is just 0. And so we're going to be left with 100 minus 20 lambda, just adding these two together, plus lambda squared minus 49 equals 0. And we'll just rearrange this to be in a typical quadratic form. So we'll have lambda squared plus 51, right? That's 100 minus 49. Oops, actually, sorry. I am very tired today. Lambda squared minus 20 lambda, and then we'll have the plus 51 to have the typical quadratic, the way the quadratic formula is usually written, okay? And then we'll solve it like we did before using the quadratic formula. We'll do the, negative b plus or minus b squared minus 4a, which is just 1, just the coefficient of lambda squared, c, and that's 51, over 2a, so over 2 and over 2. So this is going to be 10 plus or minus 20 squared, 400 minus 4 times 51, 196, and the root of 196 is 14, and 14 divided by 2 is going to be 7. So we have 10 plus or minus 7 equals lambda. So we know that lambda can either be 10 minus 7, which is 3, so we'll call lambda 3, and lambda plus equals to 10 plus 7, which is 17. So now we have our lambdas, right? These are all the lambdas again. Just to reiterate, let me highlight these again. Just to reiterate, these are the 3 lambdas that we need to have, so that we can have, so that when we're looking for the determinant of our Hessian of this matrix, of our Hessian matrix, it'd be equal to 0. When we're subtracting our Hessian matrix by our lambda matrix, and what the part here that I'm not showing you is just our Hessian matrix, the way we get the Hessian matrix minus lambda, right? Let's just write down the Hessian matrix we had before, which is hopefully you can see that 0, 0, 0, 0, 10, 7, 7, and 10, and it's minus lambda, right? Right? And the way we get this, and I won't go into too much detail about where all this comes from. This is really just to solve the problems, but it's the way we get this is just some scalar lambda times the identity matrix, which is just 1, 0, 0, 1, just 1 down the diagonal. And that's how we can, we do that so that we can subtract lambda from our Hessian matrix. So that's, if you're wondering how we get this guy, it's from this, okay? And now we've solved for the lambdas. We have lambda 1 equal to 0, lambda 2 equal to 3, and lambda 3 equal to 17. And we're going to move on to the next step, which is the eigenvectors, okay? So what's happened here is we have 3, so actually, let me go back really quick from step 4. We want to take each lambda and create a new matrix where you see lambda in our Hessian, right? When we plug lambda in here, we're going to get 3 different Hessian matrices. Okay, so now I've plugged in, so this one is for lambda equals 0, so we end up with the same matrix because it's 0 minus 0, 10 minus 0, you get the point. We have our for lambda equals 3, right? 0 minus lambda is negative 3. 10 minus 3 is 7, right? Then lambda equals 17, so negative 17, 10 minus 7 is negative 7, and 10 minus 7 again, negative 7. Okay, so now I'm going to explain to you how we get these vectors, these eigenvectors. And essentially, we just want a vector when it's multiplied by our matrices for each lambda that the result is 0. So usually it's easy just to see. So let's start with lambda 3 equals 17, right? Matrix multiplication, 17 times 0 is 0, 0 times 1 is 0, 0 times 1 is 0, result is 0. Next one, 0 times 0 is 0, negative 7 times 1 is negative 7, 7 times 1 is 7, right? And then it's a linear equation, so you add them all together. 0 plus 7, negative 7 plus 7 equals 0. Okay, and same thing for the last one, which ends up becoming 7 minus 7 is 0. All right, so we just have to, you're going to find it just by looking at it. You just take a second and you'll be able to see which vector. It's really nothing, it'll never be anything that complicated. So we do the same thing for lambda 2 equal to 3, right? Negative 3 times 0 is 0, plus 0 times negative 1 is 0, 0 times 1 is 0. Add that all together, 0, 0 times 0 is 0, 7 times negative 1 is negative 7, plus 7 times 1 is 7, negative 7 plus 7 equals 0. So, right, so we have these vectors now that when we multiply them by our matrices of lambda 1, 2, and 3, that the result is 0. Now for the eigen decomposition, we're usually going to want to have a vector with unit length 1. And so the way to get those is we're going to take, so let's say we have that we call these vectors A, B, and C. Got it. I hope you can see that. If it might be too small. But we want to take the entries for our eigenvectors and add each of them squared and then find the square root. So let's do that just so I can do complicated stuff. So let's start with the first one. So we'll have 1 squared plus 0 squared plus 0 squared. This is going to equal to 1 squared, which is just 1 altogether. And now we're going to divide our original eigenvector by this value. And in this case, we're going to be left with the same thing, 1, 0, 0, because 1 divided by 1 is 1, 0 divided by 1 is 0. Okay, let's do the next thing for the next one for this. We're going to have 0 squared plus negative 1 squared plus 1 squared. Okay, and we're going to be left with 2. Okay, and now we're going to take our vector here, and we're going to divide it by root 2. So 0 divided by root 2, that's still going to say 0, and we're going to have 1 over, which, by the way, root of 1/2 is the same as 1 over root 2, negative, because we're dividing negative 1 by root 2. And then same for the bottom, root 2, because it's just 1. 1 divided by root 2. Okay? Oh, and I forgot the half here. Shoot. 1. There we go. And same for this one. 1 squared plus 1 squared plus 0 squared is going to give us root 2 again. And so we're going to have another vector of 0, 1 over root 2, and 1 over root 2. Okay, so we have our 3 vectors here, which are, we call the unit length, because, each, I believe, each square adds up to 1 of all the entries. So a squared plus b squared plus c squared equals 1. So now we're going to build our decomposition matrix, which is the last part. And the formula for the decomposition matrix, the way you set it up, is the Hessian matrix, right? Equal to the eigenvector matrix that we found. So these are our of unit length. So these are the 3 vectors here. We form it together to make one matrix, which is this one right here, and we will call it E, times our lambda matrix, times the transpose of E. And that and these 3 multiplied by each other will result in the Hessian matrix. And in this case, the transpose of E is just the same thing. If you're wondering how I get the transpose, really quickly, right? Each each column becomes the first row. So this column becomes the first row, this column becomes the second row, and the last column becomes the last row. And as you can see, it just results in the same thing. And so when you multiply this times this times this, the resulting is our original Hessian matrix. Okay, so that was just the way to solve that. I won't go into any more time. Again, this is not a theory video. I'm not really equipped, to do all to explain all the theory as well as professors can. So you'll find that information better with them. But if you're looking on how to solve the problem, this is the solution. So thanks and have a good one.